While you were counting down to midnight, the sun was counting down to something else entirely. December 31st, 2025, 1350 UTC. An M7.1 solar flare erupted from active region 3914 and fired a billion-ton cloud of magnetized plasma directly at Earth. Arrival time, January 3rd. Impact zone, the weakest spot in our magnetic shield. But here's what nobody's talking about. At the exact moment of eruption, 5 planets were clustered in the same sector of space. A configuration that doesn't happen often. A timing that feels less like coincidence and more like a pattern we're not supposed to notice. Stay with me, because what's coming isn't just about this flare. Hit subscribe and stay with us. The flare has erupted. The plasma cloud is en route. But this is just the opening act. The planetary alignment that might have framed this eruption is still evolving. January 3rd's impact will answer some questions and raise others. Don't miss what happens next. The ball dropped in Times Square. Fireworks exploded over Sydney Harbor. Champagne corks popped across every time zone on Earth. And 9 minutes after midnight struck in London, the sun fired back with its own celebration. Except this one wasn't aimed at the sky. It was aimed directly at us. December 31st, 2025, 1350 Zulu time. While most of humanity was counting down to a new year, a region on the sun's surface, designated active region, 3914, suddenly unleashed an M7.1 solar flare. If you're not familiar with the solar flare classification system, here's what you need to know. Flares come in categories: A, B, C, M, and X, with each letter representing a tenfold increase in energy. M-class sits right below the big scary X-class events that make headlines and knock out satellites. An M7.1 is strong, not apocalyptic, but strong enough to make every space weather forecaster on Earth sit up straighter in their chair. But here's where things get interesting. The flare itself, that initial burst of electromagnetic radiation, travels at the speed of light. It hit Earth's atmosphere in 8 minutes. Satellites registered the impact immediately. Radio operators noticed brief interference. The usual stuff. What matters more, what always matters more, is what came after. Coronal mass ejections. CMEs. Think of them as billion-ton clouds of magnetized plasma ripped from the sun's outer atmosphere and hurled into space at speeds that would make a bullet train look like it's parked. This particular CME wasn't the fastest ever recorded, not even close. But speed isn't everything. Density is, and this cloud was dense, thick with charged particles, heavy with magnetic energy, moving at a pace that suggested it had staying power. No AA Space Weather Prediction Center didn't mince words. They called it a strong hit. That phrasing matters. No AA deals in probabilities and percentages. They use terms like minor, moderate, enhanced activity. When they say strong hit, people who monitor space weather for a living take notice. This wasn't a glancing blow. This wasn't a near miss that would clip Earth's magnetic field and slide past. This was a direct shot. The CME appeared as a partial halo event in coronagraph imagery. A halo means the eruption is heading toward or away from the observer. Partial means it's not perfectly centered, but it's close enough. Earth was in the target zone. What's more, side view images from Stereo A, a spacecraft positioned away from the Earth-Sun line, confirmed what ground-based instruments suggested. This cloud had width. It had structure. It was going to engulf our planet's magnetic field completely when it arrived. Now, let's talk about timing. Solar flares happen all the time during active phases of the solar cycle. Earth gets hit by CMEs more often than you'd think. Most pass without incident. A few auroras, maybe some brief GPS interference. Nothing civilization-threatening. But this eruption happened to target one of Earth's most vulnerable spots, the South Atlantic anomaly. you've probably never heard of it. Most people haven't, but satellite operators lose sleep over it. The South Atlantic Anomaly is a region off the coast of Brazil where Earth's magnetic field dips closer to the surface than anywhere else on the planet. It's a weak spot in our protective shield. Radiation that would normally be deflected at higher altitudes can penetrate deeper here. Satellites passing through this zone are more susceptible to damage. Electronics can glitch, systems can fail, and when a major CME is heading directly toward Earth, the South Atlantic Anomaly becomes a bullseye within a bullseye. Here's where the story takes a turn from notable space weather event to why is this happening now? Because the timing of this flare isn't just interesting in terms of New Year's Eve fireworks symbolism. It's interesting because of where the planets were when it happened. On December 31st, 2025, Jupiter, Earth, Mercury, Venus, and Mars were positioned in the same general longitudinal sector of the solar system. Not a perfect straight line. Planetary alignments almost never are. But close enough that if you plotted their positions on a diagram, you'd see a clustering that doesn't happen often. Add in a Saturn-Neptune conjunction occurring in the background, and you've got a configuration that makes a certain subset of researchers very quiet and very nervous. Mainstream solar physics doesn't like talking about planetary positions. There's a reason for that. For decades, the dominant models of solar activity have treated the sun as an isolated system. Sunspots, flares, CMEs, they're driven by internal magnetic dynamics, convection currents, dynamo processes. The planets? Too far away. Gravitational influence? Too weak. Coincidence? Not causation. But here's the thing about coincidences. When they keep happening, they stop feeling coincidental. Some observers, the ones willing to risk their reputations, started calling this eruption pre-aimed within hours of its detection. Not random, not spontaneous, pre-aimed. As if the sun had lined up its shot and waited for the moment when Earth would be in exactly the right position to take the full force of the impact. As if the alignment of multiple planets in the same sector of space somehow mattered. No one will say this officially. No press release from NASA is going to suggest the sun is responding to planetary positions. But the whispers are there. The data is there. And the question hangs in the air like static before a lightning strike. Why now? Why this flare at this strength, aimed at this vulnerable point on Earth, during this rare planetary configuration? If this were just a flare, the story would end here. But the clock didn't stop on New Year's Eve. Predicting when a CME will arrive is more art than science, but the models have gotten better. NOAA and NASA both ran their simulations within hours of the eruption. Different algorithms, different assumptions, different margins of error, but they agreed on the window. January 3rd, around 1100 Zulu. Give or take a few hours. That's 48 hours from eruption to impact. 2 full days of waiting. You might think the dangerous part is the moment the plasma cloud slams into Earth's magnetosphere. That's when the auroras light up. That's when power grids strain. That's when satellite operators hold their breath. But the real danger starts earlier. It starts in the waiting. CME arrival predictions work by measuring the cloud's speed and density, then calculating how long it will take to cross the distance between the Sun and Earth. About 93 million miles, give or take. Fast CMEs can make the trip in 15 to 18 hours. Slower ones like this one take longer, but longer doesn't mean weaker. In fact, slow CMEs can be more dangerous precisely because they linger. Think of it this way. A fast CME hits hard and fast, dumps its energy in a concentrated burst, then moves on. Earth's magnetosphere gets compressed, snaps back, recovers. A slow CME arrives like a heavy hand pressing down on a membrane. It doesn't spike and release. It pushes and holds, and holds, and holds. Before the main cloud even arrives, smaller disturbances reach Earth first. We call them preconditioning shocks, little pulses of faster-moving particles that got out ahead of the main mass. They're not strong enough to cause major problems on their own, but they're strong enough to start reshaping Earth's magnetic field. They stretch it, compress it, prepare it for what's coming. This is where things get subtle. Earth's magnetosphere isn't a rigid shell. It's more like a rubber band under constant tension from the solar wind. Under normal conditions, it flexes and rebounds. But if you stretch a rubber band too far for too long, it weakens. It loses elasticity. And when the big hit comes, it doesn't snap back the way it should. There's a term for this in space physics: magnetospheric softening. It's what happens when prolonged solar wind pressure degrades the field's ability to resist further compression. Historical data shows that some of the worst geomagnetic storms on record weren't caused by the fastest or most energetic CMEs. They were caused by CMEs that arrived when Earth's magnetosphere was already weakened by prior activity. December 31st's eruption wasn't an isolated event. Solar cycle 25 has been unusually active. Flares have been more frequent. CMEs more common. Earth's magnetic field has been taking hits for months, and now, just as a rare planetary alignment peaks, just as the solar system's largest planets cluster in the same sector of space, here comes another one. A strong one. A dense one. A slow one that's going to settle in and squeeze. The psychological paradox of CME forecasting is this: the closer the impact gets, the more confident the models become, and the less you can do about it. Satellite operators can put their hardware into safe mode. Power companies can balance loads across grids. Airlines can reroute flights away from polar routes where radiation exposure spikes. But there's no stopping it, no deflecting it. You just wait. And while you wait, you watch the models update. Every few hours, new data comes in, new projections, new uncertainty ranges. The forecasters at NOAA don't sleep much during events like this. They're watching plasma velocity, magnetic field orientation, density readings from upstream satellites. Because here's the thing, nobody tells you about CME predictions. The models can tell you when it's going to hit. They're pretty good at that now. What they can't tell you, not with certainty, is how hard. That depends on the magnetic orientation of the incoming cloud. If the CME's magnetic field points south when it arrives, opposite to Earth's field, you get maximum coupling, maximum energy transfer, maximum geomagnetic storm potential. If it points north, same direction as Earth's field, the impact is muted. The problem is, you don't know which way it's pointing until it's almost on top of you. So the models converged on January 3rd. They agreed on the arrival time, but the intensity projections diverged. Some suggested a moderate storm. Others warned of severe conditions. A few, the outlier models that factor in variables the mainstream ones ignore, flagged this event as potentially extreme. By January 1st, the waiting had a quality to it. Not panic, not calm. Something in between. A collective holding of breath. Because everyone monitoring this event knew the same thing. The danger window wasn't a moment. It was a process. It was the hours before impact, when Earth's magnetic field would start to feel the pressure. It was the arrival itself, when the cloud's full mass would engulf the magnetosphere. And it was the aftermath, when the slow-moving plasma would continue to pour energy into Earth's space environment long after the initial shock. And while Earth waits, something else in the solar system is lining up. Literally. Let's be very clear about what we mean when we say planetary alignment. We're not talking about a straight line. The planets are never in a perfect straight line. Orbital mechanics doesn't work that way. What we're talking about is longitudinal clustering. Multiple planets occupying the same general sector of the solar system at the same time, as viewed from above the Sun's North Pole. On December 31st, 2025, Jupiter, Earth, Mercury, Venus, and Mars were positioned within roughly 60 degrees of each other. That's a narrow slice of the 360-degree circle around the Sun. Not rare in the sense that it never happens, but uncommon enough that it's worth noting. And when you add in the fact that Saturn and Neptune were in conjunction, meaning they appeared close together from Earth's perspective, you've got a configuration that doesn't repeat often. Why does this matter? The standard answer from solar physics is, it doesn't. The gravitational influence of the planets on the Sun is negligible. Jupiter, the largest planet, is still more than 5 astronomical units away from the Sun at its closest. Its gravitational pull on the solar surface is measured in fractions of a percent compared to the Sun's own self-gravity. The other planets? Even smaller. Mathematically trivial. But here's where the conversation gets uncomfortable. Because while the direct gravitational forces are small, they're not zero. And in complex systems, especially systems already under stress, small forces applied at the right time can matter. Let's talk about Jupiter for a moment. It contains more mass than all the other planets combined. When Jupiter moves, the entire solar system's center of mass shifts. Not by much, but it shifts. The Sun doesn't sit perfectly still at the center of the solar system. It wobbles around a point called the barycenter, which is sometimes inside the Sun's volume and sometimes just outside it, depending on where Jupiter is in its orbit. This motion is called solar barycentric motion. Most people, even most scientists, don't think about it. But it's real, it's measurable. And some researchers have quietly pointed out that periods of increased solar activity, historically, seem to correlate with periods when the Sun's barycentric motion is most pronounced. Correlation, not causation. An important distinction, but correlation that keeps appearing. Now add in the other planets. Individually, their gravitational effects are tiny. But when multiple planets cluster in the same region of space, their influences don't just add, they align. They create a directional bias in the tidal forces acting on the Sun's interior. Again, small forces. But the Sun isn't a solid ball of rock. It's a roiling sphere of plasma with complex internal dynamics. Magnetic fields threading through convection zones. Differential rotation between the core and the surface. A system balanced on the edge between stability and chaos. What if those small planetary forces don't cause solar eruptions directly, but instead shift the boundary conditions? What if they nudge an already unstable magnetic structure just enough to tip it over the edge? This is the question mainstream solar physics doesn't want to engage with. Not because the idea is scientifically impossible, but because it opens a door to territory that looks uncomfortably close to astrology. For decades, the field has worked hard to distance itself from any suggestion that planetary positions influence solar behavior. The math says the forces are too small. Case closed. Except the patterns keep appearing. Large solar eruptions, when you look at historical data, tend to cluster around planetary alignments and oppositions. Not perfectly, not every time, but more often than random chance would predict. Researchers who've analyzed centuries of sunspot records and compared them to planetary ephemerides have found correlations that are statistically significant, even if the mechanism remains unexplained. The usual response is, correlation without mechanism isn't science. And that's a fair point. But it's also a way of avoiding the question. Because if there is a mechanism, if there's some resonance effect, or magnetic coupling, or tidal triggering that we don't fully understand yet, ignoring the correlations won't make them go away. So here we are, December 31st, 2025. A major solar eruption occurs while 5 planets occupy the same sector of the solar system. A Saturn-Neptune conjunction hangs in the background. And the Sun, which has been unusually active all cycle, decides this is the moment to fire a dense, slow-moving CME directly at Earth's most vulnerable magnetic zone. Coincidence? Maybe. Probably if you ask the majority of solar physicists, but the ones who've been watching these patterns for years. The ones who've built models that incorporate planetary influences, even though they'll never get published in mainstream journals. They're not surprised. They've been waiting for something like this. Because if alignments don't matter, then why do patterns keep appearing where models don't look? Science advances by building models that predict observations. When observations match predictions, confidence grows. When they don't, the model gets revised. But there's a third category, one that makes everyone uncomfortable. Observations that reveal patterns the models weren't designed to see. Solar eruptions are unpredictable. That's the standard line. We can track active regions. We can measure magnetic field complexity. We can estimate probabilities. But we can't say with certainty when a flare will happen or how strong it will be. The sun is too chaotic, too many variables, too much complexity. Fair enough. But here's the problem. When researchers go back through historical data and look at when major solar eruptions occurred, then overlay planetary positions. At those times, patterns emerge. Big flares and CMEs cluster around moments when planets are in syzygy, astronomical alignments where multiple bodies line up on the same or opposite sides of the sun. They cluster around moments when Jupiter and Saturn reach particular geometric relationships. They cluster around moments when the solar system's center of mass shifts significantly. These patterns don't appear in forecasts because the models don't include planetary positions as variables. And the models don't include planetary positions because the gravitational forces are calculated to be too small to matter. It's circular reasoning. We don't look for it because we don't think it matters. We don't think it matters because we haven't looked for it. The phrase scientists fear most in this context is correlation without mechanism. It's a death sentence for research proposals. If you can't explain how something works, proving that it happens doesn't matter. Peer review will reject it. Funding won't materialize. Careers stall. So most researchers who notice these patterns keep quiet. They publish on safer topics. They wait for someone else to figure out the mechanism. But a few have tried. The gravitational influence debate has quietly raged for decades. One camp insists that electromagnetic effects must be involved, not gravity. Maybe planetary magnetic fields interact with the solar wind in ways that feed back to the sun's magnetic structure. The other camp points out that tidal forces, even if weak, could trigger instabilities in a system already primed to erupt. It doesn't take much force to tip over a structure that's already leaning. There's a concept in physics called resonance. A small force, applied at the right frequency, can build up enormous effects over time. Push a child on a swing with tiny pulses timed to the swing's natural period, and eventually, they're soaring. The same principle applies to oscillating systems everywhere, and the sun's interior is full of oscillations. Pressure waves, magnetic flux tubes rising and falling, convection cells cycling on timescales from minutes to years. What if planetary positions matter not because they exert strong forces, but because they create resonance conditions? What if the timing of their alignments matches some natural frequency in the sun's magnetic dynamo? Here's another uncomfortable fact. Solar eruptions often lag behind planetary alignments by days or weeks. Not immediate triggers, but delayed responses. This is actually what you'd expect if the mechanism involves the solar interior. The sun's core rotates at a different rate than its surface. Magnetic fields take time to rise from deep layers to the photosphere. An influence that starts deep might not manifest as a visible eruption until much later. This delay makes statistical analysis harder. It also makes the correlation easier to dismiss. After all, if the eruption doesn't happen during the alignment, can you really say they're related? But anyone who studies earthquake triggering knows this problem well. Stress builds slowly over years. The final trigger, whether it's tidal forces from the moon or pressure from underground fluids might only add a tiny amount of stress. But if the fault was already at its breaking point, that tiny addition is enough. Maybe solar eruptions work the same way. Magnetic energy builds in active regions. Stress accumulates. The structure becomes unstable. And then, when planetary positions create just the right tidal or electromagnetic nudge, it releases. Not because the planets caused the instability, but because they provided the final push. December 31st, 2025 fits this pattern. Solar cycle. 25 has been building. Active region 3914 was already magnetically complex. The eruption was coming. The question is, why that day? Why that moment? Why when 5 planets happen to be clustered together? The models don't have an answer because the models don't ask the question. But the data point is there. Add it to the historical record. Another major eruption during a planetary configuration. Another correlation that scientists will argue about in private and ignore in public. What if the sun didn't suddenly snap? What if it was already at the edge? Let's frame this clearly from the start. What follows is not established science. It's not proven. It's not consensus. It's a hypothesis, one that a small number of researchers take seriously and the majority reject or ignore. But it's worth understanding, if only because it offers an explanation for patterns that otherwise look like coincidence. The hypothesis goes like this. The solar system is not a collection of isolated objects. It's a coupled energy environment. The sun dominates, obviously. But the planets, especially the gas giants, aren't just passive passengers. They interact with the sun's magnetic field through the solar wind. They contribute to the overall electromagnetic topology of the heliosphere. And when they align in particular configurations, they can subtly reshape the energy distribution in ways that affect solar activity. Start with something called the heliospheric current sheet. It's a vast, rippling surface that extends from the sun out through the solar system, separating regions of opposite magnetic polarity in the solar wind. During solar minimum, the current sheet is relatively flat. During solar maximum, it becomes warped and twisted. The planets, as they orbit, cross through this sheet. Their magnetic fields, where they exist, interact with it. Even the non-magnetic planets create disturbances in the plasma as they plow through the solar wind. Now imagine 5 planets clustered in the same longitudinal sector. They're all contributing to the current sheet structure in the same region of space. They're all pulling on the solar wind in roughly the same direction. The effect on any given day is small, but over weeks and months, as the configuration builds, the cumulative influence might be enough to change the magnetic topology near the sun. The math here gets complicated fast, but the principle is straightforward. Think of the heliospheric current sheet like a bedsheet held at 4 corners. Normally, with planets distributed evenly around the sun, the pulling forces balance out. The sheet ripples but maintains a relatively symmetric structure. But when multiple planets cluster on one side, the symmetry breaks. The sheet gets pulled preferentially in one direction. And because the current sheet is intimately connected to the sun's global magnetic field, changes in its structure can feed back to the solar interior. We're not talking about strong forces here. We're talking about persistent biases in magnetic pressure, tiny asymmetries that accumulate over time. The sun's magnetic dynamo operates on cycles that span years. What if those cycles are sensitive to initial conditions set by planetary configurations? What if a clustered alignment at the start of a cycle predisposes that cycle toward higher activity? Solar cycle 25 has been strange. It ramped up faster than expected. It's produced more M-class and X-class flares than the previous cycle. The sunspot number peaked earlier. Models that predicted a weak cycle have been consistently wrong. Something about this cycle is different, and nobody has a satisfying explanation for why. The standard models look at the sun's internal magnetic field generation. They consider the conveyor belt of plasma circulation from the equator to the poles and back. They factor in differential rotation rates at different solar latitudes. These models work reasonably well for predicting average behavior, but they keep missing the extremes. They underestimated cycle 25's strength. They couldn't explain why some cycles produce more geo-effective CMEs than others, with similar sunspot counts. Something is missing from the picture. Here's where the hypothesis gets speculative. What if the current planetary configuration, which has been building for the past year, has pushed the sun into a more volatile state? Not through direct force, but through boundary condition changes. The sun's internal dynamo was already producing strong magnetic fields. The alignments didn't create those fields, but maybe they created conditions where those fields are more likely to become unstable and erupt. Think of it like boiling water. You can increase the temperature slowly, and the water stays liquid. But once you hit the boiling point, the slightest disturbance, a vibration, a grain of dust, can trigger rapid bubble formation. The energy was already there. The trigger didn't add energy. It just provided the nucleation point for release. This is a concept called criticality in complex systems. You build up energy or stress over time until the system reaches a critical threshold. At that point, it becomes exquisitely sensitive to perturbations. A tiny push can trigger a massive response, not because the push was strong, but because the system was already poised to release energy. Earthquakes work this way. Avalanches work this way. Stock market crashes work this way. Maybe the solar system works the same way. Energy builds in the sun's magnetic field over months and years. Active regions form, complexity grows, and then, when planetary positions create just the right electromagnetic or tidal environment, eruptions happen. Not because the planets caused the stored energy, but because they triggered its release. The timing fits eerily well. Active region 3914 had been growing for days before the New Year's Eve eruption. Its magnetic field was becoming increasingly complex, increasingly sheared, increasingly unstable. Solar physicists watching it knew an eruption was coming. They just couldn't say when. And then, precisely when Jupiter, Earth, Mercury, Venus, and Mars reached their closest longitudinal clustering, precisely when the Saturn-Neptune conjunction was at its tightest, the region erupted. This would explain the lag time. It would explain why correlations exist, but mechanisms remain unclear. It would explain why some cycles are more active than others, independent of raw sunspot count. And it would explain why this particular M7.1 flare erupted when it did. But the hypothesis goes further. It suggests that what we're seeing isn't just about individual eruptions. It's about the overall state of the solar system's electromagnetic environment. When multiple planets align, when the heliospheric current sheet gets distorted in particular ways, when the solar barycentric motion reaches certain extremes, the entire system enters a different regime. Not permanently, just temporarily. A heightened state where fluctuations are amplified, where small instabilities cascade more readily, where the threshold for eruptions drops. If this is true, then we should expect to see other unusual behaviors during these periods. Not just solar flares. Other phenomena that reflect a noisier, more energetic environment. The hypothesis also connects to something else happening right now in the solar system. An interstellar object designated 3I Atlas, currently moving through the inner solar system, has been exhibiting unusual behavior, brightness fluctuations, trajectory anomalies. Nothing dramatic enough to make headlines, but enough to puzzle the astronomers tracking it. Interstellar objects are rare. They pass through quickly. They don't usually do anything interesting. But what if 3I Atlas is responding to the same energetic environment that's making the sun more volatile? Interstellar objects are shaped by their journey through the galaxy. They accumulate layers of frozen gases. They develop complex surface chemistry. And when they enter a new stellar system, When they encounter solar radiation and the solar wind, those surfaces respond. They outgas, they fragment, they change. Most interstellar objects pass through the outer solar system, where solar influence is weak. They come, we observe them, they leave. But 3I Atlas's trajectory brought it unusually close to the inner system. It's experiencing solar wind conditions that previous interstellar visitors didn't. And if the solar wind right now is genuinely different, more turbulent, more magnetically complex due to the planetary configuration, then 3I Atlas might be reacting to an environment that's unlike anything we've measured before. The brightness fluctuations could be outgassing events triggered by localized heating. The trajectory anomalies could be non-gravitational forces from asymmetric outgassing, similar to cometary jets, but on an object we didn't expect to behave like a comet. We're watching it respond in real time to conditions we don't fully understand, in a solar system that's behaving in ways our models didn't predict. What if the solar system right now is in a heightened state that we don't fully understand? Not apocalyptic, not civilization ending, just noisier, more active, more prone to unexpected events, like a pot of water that's been brought just to the edge of boiling. Most of the time, it looks calm. But every so often, a bubble forms. A pulse of heat reaches the surface. The system releases energy it's been accumulating. That's what the M7.1 flare might represent. Not an anomaly. Not a freak event. Just a release that happened when conditions made releases more likely. And if the hypothesis is correct, if the solar system really is in this heightened state, then we should expect more such releases. More flares, more CMEs, more geomagnetic storms, more unexpected behavior from objects like 3I Atlas that happen to be passing through at the wrong time. No one is claiming causation here. That's important. The claim is only that the timing is notable. A planetary alignment, a major solar eruption aimed at Earth, an interstellar object behaving strangely, all happening within the same narrow window of time. Scientists hate coincidences because coincidences can't be tested. You can't run an experiment to see if a coincidence is real or just random chance dressed up in pattern-seeking human cognition. But you can watch, you can collect data, you can see if the pattern holds as the configuration evolves. If the planetary alignment matters, then solar activity should change as the alignment disperses. If it doesn't matter, then activity should continue at the same level regardless of planetary positions. Over the next few months, Jupiter will continue in its orbit. The other planets will spread out. The clustering will dissolve. The Saturn-Neptune conjunction will widen. And we'll see what happens. Does solar activity decline? Does the volatility persist? Does 3I Atlas continue its strange behavior, or does it settle down? The data will come in whether we want it to or not. The universe doesn't wait for us to decide what questions are worth asking. Coincidence? Probably. But the pattern is there, and it's not just humans watching this unfold anymore. Astronomy used to be a human endeavor. Observers at telescopes. Data analyzed by hand or simple computers. Discoveries made through patience and pattern recognition by human brains trained over years of experience. That model is dying, not because humans aren't good at it, but because the volume of data has exceeded human capacity to process it. We're generating more astronomical data in a single night now than was collected in entire decades a generation ago. Wide-field survey telescopes scan the entire visible sky every few days. Solar monitoring satellites stream gigabytes of imagery every hour. Asteroid tracking networks photograph millions of objects. Stellar observatories monitor hundreds of thousands of stars simultaneously. The human eye can't keep up. The human brain can't process it all. We needed something else. Enter machine learning. Artificial intelligence trained not to recognize known categories, but to detect anomalies. Systems that don't know what a normal solar flare looks like because they've been programmed to spot abnormal ones. Algorithms that scan millions of data points per second, flagging anything that deviates from baseline patterns. The shift is fundamental. Traditional astronomy worked by hypothesis. You suspected something existed. You looked for it. You confirmed or rejected your hypothesis. Discovery was intentional. Now, discovery is accidental. The AI finds things we weren't looking for. It notices patterns we didn't know existed. It tells us something is unusual before we've even formulated the question of whether it should be. These systems are running right now. On solar monitoring satellites, on asteroid tracking networks, on telescopes watching distant stars, and they're finding things human observers would have missed or dismissed. Take solar flares. Traditional classification is straightforward. Measure the X-ray flux. Assign a letter and number. Done. But AI-driven systems are analyzing flare morphology, temporal evolution, spectral characteristics, associated CME properties. They're building profiles of what flares typically look like at every stage of a solar cycle. And when a flare doesn't fit the profile, even if its raw energy falls within expected ranges, the system flags it. The algorithms don't know physics. They don't understand magnetic reconnection or plasma dynamics. They just know statistics. They've been fed thousands of flare events and told to learn what normal looks like. Then they watch for deviations. It's pattern recognition without comprehension, and it's remarkably effective at finding outliers. The M7.1 flare on December 31st was flagged, not because it was unusually strong. M-class flares happen regularly during solar maximum. It was flagged because its buildup phase didn't match typical patterns. The magnetic field evolution in active region 3914 showed characteristics the AI had learned to associate with much larger eruptions. The flare itself underperformed, energetically speaking, relative to what the pre-eruption magnetic configuration suggested should have happened. In other words, the AI expected something bigger. It's like watching someone wind up for a punch and then pull it at the last second. The intent was there. The energy was there. Something held it back. Think about what that means. The magnetic configuration was primed for a major X-class event. The shear was there. The free energy was there. By all statistical measures based on previous similar configurations, this should have been a much larger eruption, but it wasn't. The region released only a fraction of its available energy. The rest remained locked in place, still waiting, still unstable. Does that make the event less dangerous? Maybe. Or maybe it makes it more concerning, because now you have an active region that tried to erupt, didn't fully succeed, and still contains significant unreleased magnetic energy. It's a loaded spring that only partially unwound. And loaded springs don't stay loaded forever. Human analysts reviewed the flag and shrugged. Flares are unpredictable. Sometimes they fizzle. Sometimes they overperform. The AI's expectations aren't physics. They're statistical correlations. Interesting, but not actionable. And that response reveals the tension between human intuition and machine pattern recognition. Humans want to understand why something happened. If the AI can't provide a mechanism, just a statistical expectation, then the human brain defaults to dismissing it. We're trained to distrust correlations without causation. We've built entire scientific methodologies around that principle. But what if the correlations are real, and we just haven't found the mechanism yet? But here's the thing about AI anomaly detection. It doesn't just flag individual events. It looks for clusters, patterns across multiple datasets. And in January 2026, the flags are piling up. Asteroid detection systems are reporting more near-Earth objects than expected, not dangerous ones, not impact threats, just more than the statistical baseline predicts. The solar system is full of asteroids. We discover new ones constantly as our detection capabilities improve. but the AI systems have been calibrated to account for detection bias. They know the survey patterns. They know how many objects we should be finding, based on telescope coverage and orbital dynamics. And right now, the discovery rate is elevated beyond what improved detection alone can explain. Stellar monitoring programs are catching more outbursts from variable stars, more unexpected flares from quiet stars, more transitions happening faster than evolutionary models suggest they should. We're talking about stars that have been stable for years, suddenly showing activity. Stars classified as non-variable producing flares. Binary systems changing their orbital periods faster than tidal forces should allow. None of these events breaks physics. Variable stars vary. That's what they do. Flares happen on stars with magnetic activity. Orbital periods change slowly over time due to tidal interactions and mass transfer. Everything we're seeing is possible. It's just all happening more frequently than baseline statistics predict. And it's happening now. None of these anomalies, taken individually, means anything. Stars flare. Asteroids exist. The sun erupts. But the clustering, the temporal overlap, that's what the AI notices. And it can't explain why. That's not what it's designed to do. It's designed to say, this is unusual. Figure out why. The algorithms don't editorialize. They don't speculate. They don't propose mechanisms. They just calculate probability distributions and flag deviations. The current deviation level across multiple astronomical datasets is significant, not extreme, not off the charts, just enough above baseline to be statistically noteworthy. And that's precisely the kind of signal humans are bad at taking seriously. We're good with extremes. If every star in the sky suddenly doubled its brightness, we'd notice. If asteroids started raining down, we'd respond. But a 15% increase in anomalous stellar events? A 12% uptick in asteroid discoveries beyond detection bias? That's the kind of subtle shift that gets filed under interesting if true, probably just noise. Check back in 6 months. The AI doesn't have that luxury. It doesn't know to wait 6 months. It reports what it sees now. Humans don't like being told something is weird without an explanation. We want mechanisms. We want causes. AI doesn't care. It just reports the deviation and moves on to the next dataset. This shift from prediction to early warning is creating discomfort in the scientific community, because early warning without understanding feels like astrology. It feels like pattern matching without physics. And science is supposed to be about understanding, not just correlation. Astrology says planetary positions matter because of ancient symbolic associations. No mechanism, no physics, just correlation dressed up as causation. Scientists rightly reject it. But what happens when your AI, which has no concept of astrology, no cultural bias, no symbolic thinking, starts flagging patterns that look uncomfortably similar? What happens when the machine notices that solar activity spikes during certain planetary configurations? Not because it believes in astrology, but because that's what the data shows. You can't accuse an algorithm of confirmation bias. It doesn't have beliefs to confirm. You can't say it's seeing patterns that aren't there because of cultural conditioning. It doesn't have culture. It just has numbers. And the numbers are showing patterns. That's deeply uncomfortable for researchers who've spent careers explaining why planetary positions don't matter. Because if the AI is right, if there really are correlations there, then either the AI is finding spurious patterns in noise, which means our anomaly detection algorithms need recalibration, or the correlations are real and we don't understand why, which means our models of solar system dynamics are incomplete. Neither option is appealing. But the AI doesn't have that bias. It doesn't care whether planetary alignments are supposed to matter. It just watches for patterns. And right now, across multiple systems, the pattern is things are noisier than they should be. The noise isn't random. That's the key point. Random fluctuations average out over time. They don't cluster. They don't show temporal correlation across unrelated phenomena. What we're seeing is structured deviation. Multiple systems showing elevated activity in the same time window. That suggests either a common cause or a coupled response to shared boundary conditions. The AI can't tell you which. It can only tell you the pattern exists. 3I Atlas, the interstellar object, was identified by an AI-driven survey that looks for moving points of light against the stellar background. Its unusual behavior, the brightness fluctuations and trajectory oddities, were flagged by anomaly detection algorithms before human astronomers took a closer look. We don't know what's causing its behavior. We don't even know for sure what 3I Atlas is made of. But the AI knows it's doing something objects like it don't usually do. We've only detected a handful of interstellar objects. Oumuamua in 2017, Borisov in 2019. Each one was strange in its own way. Each one challenged our assumptions about what interstellar visitors should look like. 3I Atlas is the third, and it's behaving differently from the previous two. The AI caught it because its light curve, the pattern of brightness variation over time, doesn't match comets, doesn't match asteroids, doesn't match any template in its training data. Is it responding to the same energetic environment that's making the sun more volatile? We have no way to know, but the timing is notable. An interstellar interloper exhibiting unusual behavior while passing through an inner solar system that's experiencing elevated activity levels. Two anomalies happening simultaneously. The broader implication is unsettling. Humans are losing narrative control of discovery. We're finding things we didn't know to look for. We're being told that things are unusual before we understand why. And in a universe that operates on timescales far longer than human civilization, that might be the new normal. For all of human history, we've discovered things by looking for them. We hypothesized, we predicted, we searched, we confirmed. The universe responded to our questions. Now, the universe is volunteering information we didn't ask for. The AI is telling us things are happening, and we're scrambling to figure out what questions we should have been asking. This is the future of astronomy. Not humans at telescopes making careful observations and testing hypotheses, but algorithms running continuously, flagging deviations, generating alerts, while humans try to keep up with the pace of discovery and figure out what it all means. When systems start behaving unpredictably, it's rarely just one system. Let's zoom out, way out. Forget the M7.1 flare for a moment. Forget the planetary alignment. Forget 3I Atlas. Look at the bigger picture. What's the pattern? 2025 to 2026 has been a period of unexpected behavior across multiple domains. The sun is more active than predicted. Interstellar objects are passing through with unusual frequency and strange characteristics. Stellar monitoring programs are catching more outbursts, more transient events, more rapid changes than baseline models anticipated. Magnetospheric compression events at Earth are happening more often. Geomagnetic storm intensity is higher than the raw solar wind data suggests it should be. Take a moment to absorb what that means. Each of these observations, by itself, is explicable. Solar cycles vary. Some are stronger than others. We've known that for centuries. Interstellar objects have probably been passing through the solar system for billions of years. We're only detecting them now because our telescopes have gotten good enough. Stellar outbursts happen. They're part of normal stellar evolution. Geomagnetic storms fluctuate based on complex interactions between the solar wind and Earth's magnetosphere. All true, all reasonable. But here's what's nagging at the researchers who pay attention to these things. The deviations aren't random. They're not scattered across time. They're clustered. They're happening now in this narrow window across multiple unrelated systems. None of these things, individually, breaks physics. None of them is impossible. But collectively, they paint a picture of a solar system that's noisier, more dynamic, more prone to sudden state changes than our models account for. Why? That's the question nobody can answer with confidence. Complex systems, by their nature, breed instability. When you have multiple interacting components, feedback loops, nonlinear responses, predicting behavior becomes impossible beyond a certain timescale. Weather is like this. Economies are like this. Ecosystems are like this. And apparently, so is the solar system. We've gotten comfortable thinking of the solar system as a clockwork mechanism. Planets orbit in predictable paths. The sun cycles through activity phases on an 11-year rhythm. Comets return on schedule. Everything follows Newton's laws and Maxwell's equations. Plug in the initial conditions, run the simulation forward, get reliable predictions. It works beautifully for centuries-long timescales. Jupiter will be in the same place in its orbit 100 years from now as our models predict. We can eclipse predictions decades in advance, down to the second. But that predictability applies to the large-scale mechanics. Positions, orbits, gravitational interactions. When you start looking at electromagnetic phenomena, plasma dynamics, magnetic field evolution, the clockwork model breaks down. These systems are chaotic in the technical sense, sensitive to initial conditions, prone to sudden transitions between states, governed by equations that have multiple solutions, and which solution manifests can depend on tiny perturbations. Modern science excels at understanding averages. We can tell you the average solar cycle length, the average CME speed, the average geomagnetic storm intensity for a given solar wind condition. But averages hide extremes, and extremes are where the interesting, dangerous, and unpredictable stuff happens. Here's a statistical truth most people find counterintuitive. The average tells you where the bulk of the distribution sits. It doesn't tell you about the tails. And in complex systems, the tails matter more than the average. The 100-year flood causes more damage than 99 years of normal rainfall. The market crash wipes out decades of steady gains. The Category 5 hurricane is remembered long after 1,000-mile storms are forgotten. The solar system has tails in its distributions too. Extreme solar storms, massive CMEs, geomagnetic events that compress Earth's magnetosphere to half its normal size. These events are rare. The models predict them as statistical outliers. But what if the distribution itself is changing? What if the tails are getting fatter? What if events we classified as 1 in 100 are becoming 1 in 10? That's the uncomfortable question sitting beneath all of this. Are we watching normal variability, or are we watching a shift in the baseline? Nonlinear systems fail suddenly, not gradually. You can push them, and they absorb the stress. They adapt, they flex, and then, without warning, they snap. The straw that breaks the camel's back isn't heavier than the previous straws. It's just the one that happened to arrive when the system couldn't take any more. Engineers know this. They design bridges with safety factors precisely because materials don't fail linearly. A beam can hold 90% of its maximum load indefinitely. At 95%, it starts to show microscopic cracks. At 99%, the cracks propagate. At 100.1%, catastrophic failure. The difference between safe and collapsed isn't gradual degradation. It's a threshold. Maybe the solar system has thresholds too. Maybe there are energy levels or magnetic configurations or orbital resonances that, when crossed, shift the entire system into a different dynamical regime. Not permanently, not irreversibly, just temporarily, until conditions relax back below the threshold. But while you're above it, all bets are off. Eruptions become more frequent. Storms become more intense. Systems that looked stable start showing instability. Maybe that's what's happening now. Maybe the solar system has been accumulating stress, energetically speaking, for years or decades. Magnetic fields building in the sun. Planetary positions shifting into rare configurations. Interstellar medium conditions changing as the solar system moves through the galaxy. Small things, individually trivial, but collectively pushing the system toward a state where unexpected events become more common. The solar system is moving through the galaxy at over 200 kilometers per second. It's not sitting in static space. It's plowing through the local interstellar medium, a tenuous gas of atoms and magnetic fields that fills the space between stars. That medium isn't uniform. It has structure, density variations, magnetic field variations. As we move through it, the pressure on the heliosphere changes. The shape of the bubble that the solar wind carves out changes. Right now, based on measurements from the Voyager probes and IBEX satellite, we know the heliosphere is asymmetric. It's compressed on one side, stretched out on the other, responding to external pressure from the interstellar medium. Could that external pressure be feeding back to the sun's internal dynamics? Could changes in the heliospheric boundary be affecting magnetic field generation deep in the solar interior? We don't know. The timescales involved are long. The sun's convection zone turns over on a timescale of months to years. Changes in external boundary conditions might take a solar cycle, or more to propagate through the system and affect surface activity. Cause and effect get blurred when the lag time is measured in years. The M7.1 flare isn't the story. It's a data point. One more event in a growing list of things that are happening when models say they shouldn't, or not as often as they are, or not in the way they are. Add it to the list. Solar Cycle 25. Being stronger than predicted. Multiple interstellar objects detected in just a few years when we'd gone all of human history without seeing any. Stellar activity upticks across unrelated monitoring programs. Geomagnetic coupling efficiency higher than solar wind parameters alone can explain. AI systems flagging anomalies they can't explain across multiple datasets. Each data point alone is a curiosity. Together, they start to look like a pattern. Revisit the planetary alignment, not as a cause, but as context. 5 planets in the same sector of space, a configuration that happens, but not often. Does it mean anything? Maybe not. But if the solar system is a coupled energy environment, if subtle influences matter when systems are already stressed, then timing starts to look less like coincidence and more like signal. The alignment didn't create the M7.1 flare. The magnetic energy was already there in active region 3914. The alignment didn't build that magnetic structure, but maybe, just maybe, it provided the final nudge that tipped an already unstable configuration over the edge. Not cause, context, boundary condition. The trigger that mattered only because the gun was already loaded. Revisit 3I Atlas, an interstellar object exhibiting behavior we can't fully explain. Is it related to solar activity? To planetary positions? We have no mechanism to connect them. But it's happening now, in the same narrow time window. Another data point. If the solar system is in an elevated energetic state, if the heliospheric environment is genuinely noisier right now, then incoming interstellar objects would experience that changed environment. They'd encounter different solar wind conditions than interstellar objects passing through during quieter periods. Would that be enough to explain 3I Atlas's unusual behavior? Maybe. Or maybe 3I Atlas is just weird for reasons that have nothing to do with where or when it's passing through. We're comparing a sample size of 3 interstellar objects. That's not enough data to say what's normal and what's not. But the timing is there. And timing, when it clusters, demands attention. The pattern isn't proof of anything. It's an invitation to ask different questions. What if rare events don't stay rare? What if the baseline is shifting? What if the models we've built on decades of relatively stable solar system behavior are about to encounter conditions they weren't designed for. Our models are trained on historical data. They assume the future will resemble the past. That assumption works beautifully in stable systems. It fails catastrophically when systems transition to new states. Climate models built on 19th century data didn't predict 21st century extremes until those extremes started happening and got incorporated into the training sets. Economic models built during growth periods failed to predict recessions. Seismic hazard models based on recent history underestimate the risk of earthquakes that haven't happened in living memory. The solar system has a long memory. Its dynamical timescale spans millennia. Our observational record spans decades, maybe centuries for some phenomena. We're trying to characterize a system that operates on timescales we haven't observed. We're building models from a tiny snapshot of its full behavioral range. What if we're about to see behaviors that aren't in our training data? January 3rd, 2026. The dense CME from the New Year's Eve eruption arrives. Earth's magnetosphere compresses. Auroras light up skies far south of where they usually appear. Power grids strain, satellites glitch, and then, hours later, it's over. The cloud passes. The magnetosphere rebounds. Life goes on. No catastrophe. No civilization-ending disaster. Just another geomagnetic storm, stronger than most, but far from the strongest on record. Infrastructure held. Satellites survived. The power grid operators who'd been on alert managed their loads successfully. By January 4th, the event was already fading from the news cycle. Another space weather event, another close call, another reminder that we live on a planet bathed in radiation from a variable star. But the question remains, not about this flare, about the next one, and the one after that. About what it means when systems that seemed predictable start behaving in ways we didn't anticipate. About whether we're watching the early signs of a shift we don't yet understand. Because if the solar system really is entering a more volatile phase, if the baseline is shifting, then our risk calculations are wrong. Infrastructure designed to withstand once-per-decade events might face once-per-year conditions. Satellites built to survive typical solar storms might encounter atypical ones. Power grids engineered for average geomagnetic-induced currents might see extremes. We plan for the past. We prepare for what we've already seen. And when the system shows us something new, we scramble. This flare isn't the story. It's a signal. A data point in a pattern that's getting louder. And whether we like it or not, whether we understand it or not, the universe doesn't care about our models. It does what it does. And we watch, and we wonder, and we wait for the next anomaly to appear. The waiting is the hardest part, because we know with absolute certainty that the next anomaly is coming. We just don't know when. We don't know what form it will take. We don't know if it will fit the pattern or break it. All we can do is keep watching, keep collecting data, keep asking questions that don't have answers yet, and hope that when the answers finally come, we're ready for what they tell us.